Hi, my name is Edward, and this is the final challenge for Team 3. For this final challenge, we were given a realistic car simulator called Test, built in Unity, with realistic physics. For example, the car would shake at high speeds. We were also given 2 LiDARs, multiple cameras, and no max speed for the car for the various challenges. Speaking of the challenges, we had 2. The first one was a speed test, meaning we had to traverse the given trajectory as fast as possible while minimizing collisions with obstacles. The second challenge was an obstacle avoidance test. We were given a much simpler trajectory because the focus of this challenge were to avoid the randomly generated obstacles. All the obstacles, however, were of the same geometry, size, and dimensions, and they were no bigger than the width of the car. For the first challenge, the speed test, there were roughly 3 steps. We verified the localization from Lab 5. Then we hard-coded a trajectory or path that the car would take. We had an overarching path that we needed to complete, but to maximize our speed according to the physics of the car and our controller, we hard-coded a trajectory rather than using a path planning algorithm like a PRM. Lastly, we modified our Pure Pursuit controller because this was a new car in a new simulation environment, and we were going at different speeds. For the obstacle avoidance test, we decided on a simple heuristic, which will be explained more in detail later, but mostly because all of the obstacles were the same and were no bigger than the width of the car. We decided to go left if there was an obstacle on the right. We decided to go right if there was an obstacle on the left. This was analogous to the node hierarchy in Lab 3. In Lab 3, we had a safety controller that would kick in or override the command sent by the wall follower controller if it was in the immediate vicinity of danger. If the car sends danger, the safety controller would take over. Similarly, our safety controller would take over if we were within a certain threshold that we had to set, which we had to optimize and will be talked about later in the following sections. We also hard-coded a trajectory for this challenge, but it was simply a straight line because of the map previously. Now we'll talk about the speed test.
Hi, so for the speed test and Pure Pursuit, our algorithm consisted of 3 main factors: the look ahead, the determining the speed of our car, and the actual trajectory being followed. So for the look ahead, we first figured out how to go from our given trajectory to determine the point that we try to follow in our Pure Pursuit algorithm. So even though our car tries to follow the trajectory, it won't always be exactly on the path. So what we first do is approximate the car's location with the closest point to it on the path. We then take a point 15 meters ahead of it in the path, which is calculated using straight line distance as the destination, and return this to the Pure Pursuit algorithm as the point we're trying to approach. And as we move, this point will hopefully go forwards.
Okay, so the main objective of the speed challenge was to complete the course as fast as possible without colliding into objects in the simulation. Therefore, we knew we would have to implement some type of speed controller to manage turns, which are places on the track where the car is most likely to crash. Our strategy was to maximize the speed of our car on the straightaway sections and lower our speed as we approach the turn to maintain that speed throughout the turn, as shown in the figure above. In order to detect turns, we use the fact that as the car approaches the turn, the look-ahead point is at a greater angle from the heading of the car, compared to being close to 0 for straight sections. Therefore, we developed a speed function that was dependent on that angle. So the equation above demonstrates the relationship between the angle to the look-ahead point and the speed published to the car. The minimum function takes the minimum between 1 and the speed function, which is defined as 1.2 over 1 plus the absolute value of the look-ahead angle times a factor of 200. This function decreases greatly as the look-ahead angle increases and approaches 1.2 as the angle goes to 0. When the speed function is less than 1, meaning that the car is approaching a turn or at a turn, then the speed published is a small fraction of the maximum speed. On the other hand, when the speed function is greater than 1, meaning that the car is on a straight path, then the speed corresponds to 1.2 times the max speed. Additionally, we also modified our previous controller to have a KP value of 0.3 to mitigate the look-ahead angle and account for higher speeds. Next, Guanwei will talk about building the trajectory.
Thanks, Aaron. The trajectory dictates the path of the car. We first built our trajectory using the Trajectory Builder launch file from Lab 6 and publishing points in ArcViz. The trajectory was quick to build, but unfortunately, we ran into issues. If we messed up a point, it was difficult for us to correct it. We also quickly realized that the car wasn't finishing the track in the required time. When we tried to increase its max speed so that it goes faster in the straight paths, it wasn't able to make some of the turns. And if we try to make it slower, it wasn't going to finish in time. Next slide, please. So when we realized that our trajectory wasn't working, we first built our trajectory piece by piece. This ensured that we were building a valid trajectory, and if anything was wrong, we could easily correct the last point. And this can be seen on the figure on the right. And next slide, please. Thank you. And then additionally, we found this type of a trajectory to be very effective in making tight turns. We think that it's because the car looks ahead and sees that it has a turn before the actual turn. And then the structure of the trajectory allows the car to kind of drift and turn basically in a 90-degree angle. We also found that making the trajectory closer to the side opposite to the corner helps make the turn. For example, if you look at the image on the right, we see that the car is about to make a right turn, so our track is closer to the left side of the road. Next, Mac is going to talk to you about the obstacle.
Thanks, Guanwei. So yeah, we'll move on to obstacle avoidance now. At a high level, we used Pure Pursuit as our default controller, but swerved when we encountered an obstacle. On the left, you can see some pseudocode demonstrating this process. If the car recognizes a right side obstacle, it swerves left, and vice versa. If no obstacle is detected, it follows the original trajectory using Pure Pursuit. We established this hierarchy between Pure Pursuit and our swerve mechanism using a node, such that Pure Pursuit is the default, but swerve takes over if an obstacle is detected. We detected obstacles by using our car's hood LiDAR. We scanned the right and left sides separately to find out which side of the car the obstacle was on. For each side, we checked about 27 degrees worth of points in front of the car to see if they were closer than our threshold distance of 3 meters. If more than 30% of these points were less than 3 meters away, the car would initiate a swerve in the opposite direction. So like I said, once an obstacle is detected, we would swerve until the obstacle no longer falls within that 27-degree scanning range in front of the car, at which point Pure Pursuit would take over again. When swerving, we found empirically that a steering angle of 26 degrees and a velocity of 3 meters per second were most effective. So one issue we kept running into was trying to find the right balance of how much to turn. Sometimes one steering angle caused the car to turn too much for some obstacles and too little for others. Also, since the car wasn't checking for obstacles directly to its sides, we ran into a few rare cases where the car would turn into an obstacle that it hadn't detected. Both of these issues could probably be improved with finer tuning of our controller, but additionally, we could make our steering angle a function of the distance to the obstacle and the obstacle's width to make sure we're tuning exactly as much as we need to, no more and no less. With that, I'll turn it over to Jack to finish up our briefing.
Thank you, Mac. So as for some lessons that we learned, firstly, don't underestimate the time needed to set up software. I personally took many hours and discovered that using the TESS Rossbridge Ultralight worked for me rather than using the regular Rossbridge, which seems unusual and is a testament to the variety of issues that you can encounter when setting up software. Because of this, we had less time to implement on some of the challenges. Secondly, applying to a specific context the concepts and algorithms we learn results in a tedious fine-tuning, whereas generalized contexts rely on writing algorithms. For example, in the speed test, we had a single trajectory to follow, and thus we could hard code the trajectory. But in a real situation with an autonomous car, it could not possibly hard code the immense space of possible paths from all the possible starting and endpoints in a given city, for example. In conclusion, our speed test was generally successful. Our best test concluded in about 62 seconds, and we had one collision, if I'm not mistaken. We placed roughly 8th place out of 15 teams. The obstacle test, however, did not go as well, and we hit multiple objects. This could be due to a variety of reasons, as Aaron mentioned earlier. It could be tuning our parameters. We could make the angle a function of our distance to the object, or we could just do a full semicircle, as illustrated by Mac earlier, rather than having an over-reliance on the pure pursuit controller. Thank you.